let us discuss rotational Raman spectra of linear and symmetric top molecules. In rotational Raman spectroscopy, a key difference between a linear molecule and a symmetric top molecule lies in the selection rules for rotational transitions, in which the linear molecules exhibit a selection rule of del J equals plus or minus 2, meaning the rotational quantum number J can only change by 2 units during a Raman scattering event, while a symmetric top molecule can have more complex pattern depending on the specific rotational quantum numbers involved, including changes in K, that is, the projection of J onto the symmetry axis. Due to the symmetry of the polarizability ellipsoid, only transitions with del J equals plus or minus 2 are allowed, resulting in a simple spectrum with evenly spaced lines. The rotational Raman spectrum of a linear molecule is a series of lines that appear when the molecule changes its rotational energy. The selection rule for rotational Raman spectra of linear molecule is del J equals 0 plus or minus 2, where J is the rotational quantum number. The polarizability of a molecule must be anisotropic, meaning it is not the same in all directions. This is because the polarizability ellipsoid of a linear molecule changes shape during the rotation. When a molecule gains rotational energy from a photon, the scattered light loses energy and the lines appear at lower wave numbers. These are called Stokes lines. When a molecule loses rotational energy to a photon, the lines appear at higher wave numbers. These are called anti-stokes lines. The essential condition to have a vibration or rotation Raman active, the molecule must cause a change in the molecular polarizability. The rotational energy levels of linear and diatomic molecule are given by epsilon J, which is equal to Bj times J plus 1. Bj times J plus 1 per centimeter, where J goes with 0, 1, 2 goes on, where B is a rotational constant and J is a rotational quantum number. The selection rule is considered to be del J equals 0 or plus or minus 2. Only del J is the change in rotational quantum number, and plus sign is for anti-Stokes line and minus line is goes for Stokes line. Del J equals plus or minus 2 means the rotational quantum number can only change by 2 units during the scattering process, whereas for microwave spectroscopy del J equals plus or minus 1. And here del J equals 0 represents the Rayleigh line, that is, there is no change in del J. Del J equals plus or minus 2 represents the Raman lines, which is nothing but Stokes and anti-Stokes lines. Del J equals J upper state minus J lower state. That is, del J represents a change in quantum number. So, which is nothing but J upper state minus J lower state. For del J equals 2, that is, del epsilon equals epsilon J plus 2 minus epsilon J. And we know the expression for epsilon J is given as Bj times J plus 1. You substitute for J plus 2. You just instead of J, you substitute J plus 2 and get the expression. So that will give us Bj plus 2 times J plus 3 minus the lower state, which is nothing but Bj times J plus 1. And this can be written as J square plus 5J plus 6, the first term, and second time as it is minus J square minus J. pulling B common out. So J squared and J squared will get cancelled. 5J minus J will give you 4J. So B times 4J plus 6 per centimeter, which is nothing but our del epsilon, change in epsilon. And here is J is the rotational quantum number in the lower state. Wave number of the scatter radiation is given by nu S equals nu exciting radiation plus or minus del epsilon. So which is equal to, substituting for del epsilon in this equation 3.24, we have new excitation line plus or minus B times 4J plus 6 per centimeter. Here nu Ex is the wave number of exciting radiation. The positive sign refers to the anti-Stokes line and the negative sign refers to the Stokes line. If the molecule gains the energy from the photon during the collision, we will have the lines on the lower wave number side of the exciting line, which corresponds to the Stokes line. If the molecule loses energy to the photon, the lines will appear on the higher wave number. So here we will have lower wave number. So what we call this a Stokes line, and higher wave number represents the anti-Stokes line. Using equation 3.23, del epsilon equals B 4J plus 6. So substitute J equals 0 here. So we will have del epsilon equal to 6B per centimeter. And 6B is the distance from the Rayleigh line, either side. And we have the Stokes line on left hand side, and we have a Rayleigh line at the center, and right hand side we have anti-Stokes line. The distance, the first distance from the Rayleigh line, that's the separation of the first anti-Stokes and Stokes line from the Rayleigh line, is nothing but 6B. Now using equation 3.24, so we have nu S equals nu Ex plus or minus del E, and substitute for del epsilon. So that will give us nu S, which is equal to nu excitation radiation plus or minus 6B. You substitute again J equals 1 here. You substitute J equals 1. So we have del E which is nothing but 10B. J equals 2, substitute J equal to, we have del epsilon equal to 14B. Substitute J equals 3, we have del epsilon equal to 18B. And just look at the variation. So the difference is nothing but 4B on either side. So it implies that the separation of the first anti-Stokes or Stokes line from the Rayleigh line is 6B per centimeter, whereas the separation between successive anti-Stokes and Stokes line is nothing but 4B per centimeter. The following picture shows schematically the allowed transitions and the rotational constant spectrum exhibited by a linear molecule. The Raman shift of the first Stokes and or anti-Stokes lines from the exciting line is 6B per centimeter. The separation between successive lines on either side of the exciting line is 4B per centimeter. The Stokes and anti-Stokes line appear with considerable intensity as all the rotational levels belong to nu equals 0 vibrational state, which makes all the levels reasonably populated. Molecule having the larger moment of inertia may not give you a well-resolved rotational spectrum, as B will be very small for such systems. However, for diatomic and other light linear molecules, the spectrum will normally be resolved, and the measurement of the separation allows the determination of B, which in turn gives the interatomic distances. And this is the picture, and this is the figure 1 is figure 1 represents the allowed transitions between the rotational energy levels of linear molecule. And you just look at the variation. So this is plus or minus 2 jump. See, this is 2 times jump from 0 to 2, and here 1 to 3 and 2 to 4 So this is for the absorption and this is for the emission, and transition gives a Stokes line on this side, and similarly we can have the transition on this side also. So this is exact like a plus or minus 2. So 2 unit jump. And figure B shows the rotational Raman spectra, and we have the Rayleigh line at the center, which is nothing but nu naught, and the first distance from the Rayleigh line to either Stokes line and anti-Stokes line is nothing but 6b, and subsequently we have the difference is nothing but 4b, where b is the rotational constant. We have already seen that homonuclear diatomic molecules do not give an infrared microwave spectrum. However, such molecules give pure rotational Raman spectra since the polarizability changes during the rotation motion. Therefore, Raman spectroscopy may be used as a method for obtaining molecular parameters for homonuclear diatomic molecules. Another interesting feature observed is the effect of nuclear spin on the spectra of molecules having the center of symmetry as in infrared spectra. It is known that the levels with even J values are empty in molecules like O2 and CO2, that is nuclear spin of oxygen is 0, and therefore transitions labeled 0, 2, 4 in the figure will be absent. Consequently, a spacing of 8b between consecutive lines is observed instead of 4b. In the case of molecules made up of nuclei with non-zero spin, for example H2, CH triple bond with CH, and having a center of symmetry, the spectral lines show an alternation of intensities. Now let us discuss Raman spectra of symmetric top molecules. In symmetric top molecules, the rotation energy level of a symmetric top molecule is given by nu equals bj times j plus 1 plus a minus b k squared. Now we have included k. So this is k is here, and this k represents the angular momentum over the top axis. And here a and b are rotational constants, and of course j is the rotational quantum number. The selection rule is nothing here is nothing but j equals 0, 1, 2, and k equals 0 plus or minus 1 up to plus or minus j. And plus sign indicates it shows the clockwise direction, and minus sign is anti-clockwise direction about the molecular symmetry. And the selection rule is nothing but del k equals 0 and del j equals 0 plus or minus 1 plus or minus 2. Del j equals 0 represents the Rayleigh scattering. Del j equals plus 1 represents the R branch lines, Raman line, and del j equals plus 2 for S branch line, again one of the Raman lines. As del k equals 0 implies that the rotations about the top axis does not produce a change in the polarizability, whereas end over end rotation produce a change. Hence, the rotations about the top axis are Raman inactive. Since k equals 0 for the ground state, it is governed by the selection rule del j plus or minus 2 only. For j equals 1, 2, 3 up to k will have values other than 0, and del j plus or minus 1 transitions are allowed. Then restricting only to positive del j, we have del j which is equal to plus 1, that is the transition from 0 to 1 and 1 to 2, and 0 to 1 represents the R branch, 1 to 2 represents the S branch. And the change in frequency number, which is the transition from j to j plus 1, is given as nu j plus 1, which is the higher state, minus nu j, which is the lower state. You substitute instead of j, you substitute j plus 1. So we have b j plus 1, j plus 2 minus bj times j plus 1. So the first term becomes, taking B common out, we have J square plus 3J plus 2, keeping minus sign inside. So we have minus J squared minus J. J squared and J squared will get cancelled. 3J minus J will give you 2J. So B 2J plus 2, taking 2 out, we'll have 2B times J plus 1 per centimeter. So the Stokes line represents nu equals nu naught minus 2B times J plus 1, and anti-Stokes line represents nu equals nu naught plus 2B J plus 1. So put together we can write as nu equals nu naught plus or minus 2B times J plus 1 per centimeter. And this term represents a Raman displacement from nu naught, where J equals 1, 2, 3, and this gives equation 3.29. Stokes lines refer as the molecule absorbs energy from the incident photon, whereas the anti-Stokes lines denote the molecule loses energy to the incident photon light. So using equation 3.29, so we have 3.29 here. So J equals 1, you substitute J equals 1, and we have nu equals 2B 1 plus 1, which is equal to 4B. And 4B is nothing but the distance of the first line in the x-axis of the Raman spectrum in the transition from J to J plus 1. When J equals 2, we have nu equals 6B. When J equals 3, we have nu equals 8B. These are all the values in the x-axis of the Raman spectrum in the transition J to J plus 1. So now the second one, 1 to 2. So we have now when del J equals plus 2, which represents the S branch lines, del U equals nu J plus 2 minus J. So substitute instead of J, you substitute J plus 2. So we have B times J plus 2, J plus 3 minus Bj times J plus 1. So first term becomes pulling B common out. So J squared plus 5J plus 6 minus J squared minus J plus J squared minus J squared will cancel. We have 5J minus J, that will be 4J. So B times 4J plus 6. So the Stokes line represents nu equals nu naught minus B 4J plus 6. Anti-Stokes lines denote J equals nu naught plus B times 4J plus 6. So put together we have nu equals nu naught plus or minus B times 4J plus 6 per centimeter, and this term, second term, represents the Raman displacement from nu naught. Now using equation 3.32, you substitute J equals 0, and we have nu equals 6B. And when J equals 1, and this gives nu equals 10B. When J equals 2, nu equals 14B. And look at the variation. See, look at the difference between these two. It is 4B, and here also we have 4B. So when del J equals 2, the distance, that is a separation, this is nothing but 4B. So these are all the values in the x-axis of the Raman spectrum in the transition from J to J plus 2. Thus we have two series of lines in the Raman spectrum for hydrogen top molecules with del J equals plus 1, P branch lines, and del J equals plus 2, which is nothing but S branch lines, respectively as nu P, which is equal to nu naught plus or minus 2B J plus 1, and nu S equal to nu naught plus or minus B times 4J plus 6. So when J equals 0, you substitute substitute here J equals 0 in this expression. So nu P becomes plus or minus 2B, and nu S becomes 6B. Your J equals 1, nu P becomes 4B, and this is 10B. And we have 6B, 8B, 10B for J equals 2, 3, 4. And similarly, nu S becomes 14B, 18B, plus or minus 22B. And this picture, the first picture shows the Raman spectra Raman lines for R branch lines, and this is for S branch lines, and this is for the complete one. That is, we have added these two and we have obtained the third figure. So first we look at figure A. So all the things, they refer Raman spectra of symmetric top molecule. And the first picture, figure A, shows the R branch lines appear at 4B, 6B, 8B, 12B from the exciting radiation. So this is the exciting line. Now look at the difference. This is nothing but 2B. So here we have drawn the lines. This is for the Stokes line and this is for the anti-Stokes line. So look at the first one. This is 4B. The next line is 6B. And the next line is the 8B. So the difference between first line and second is nothing but successive line also is nothing but 2B. And for the S branch, look at the S branch. The difference between these two is nothing but 4B. See here 4B. The first line is nothing but 6B. The second line is 10B and third one is 14B. Now, and this is for del J equal to plus 2 and this is for del J equals plus 1. So figure A is for del J equals plus 1 and figure B stands for del J equals plus 2. Now, we are going to add these two and get the complete rotational Raman spectra of symmetric top molecule. So this is the complete one. And now we shall add. And this, the variation is nothing but, the difference between two lines is nothing but 4B and here it is 2B. 2B variation is there, here it is 4B variation is there. Now we are going to add these two now. So 4B, here there is no 4B. So 4B is here. See, we are going to add these. Now here we have 6B and here also we have 6B. So look at the line, see, this is somewhat enlarged. And we are going to add these 6B and 6B and that is the enlarged line. And here 8B alone is there, here there is no 8B, so 8B as it is. Now we have 10B is here, here also we have 10B. So we are going to add these two, so we have enlarged line. So like that we are going to add to get the complete rotational Raman spectra of symmetric top molecule. SR branch. In a rotational Raman spectrum of a linear molecule, the SR branch refers to the Stokes lines arising from a selection rule of del J equals plus 2, meaning the molecule gains 2 units of rotational quantum number during the scattering process, resulting in a series of lines spaced apart by a constant energy difference on the lower side, which is nothing but Stokes line of the exciting laser line, while the corresponding anti-Stokes line, where the molecule loses rotation energy with the same del J equals plus 2 selection rule, would appear on the higher frequency side, also forming an SR branch, but with lower intensity due to the lower population of higher rotation energy levels. The spacing between lines in the SR branch is relatively constant and directly related to the rotational constant B of the molecule. The intensity of the lines in the SR branch generally decreases with increasing rotational quantum number due to the Boltzmann distribution of rotational energy levels. Raman active and inactive molecules. Now let us learn what kind of molecules will show rotational and vibrational Raman spectra. Rotational Raman spectra. Rotational transitions are Raman active for any molecule with an anisotropic polarizability. That is, rotation will cause the change in polarizability, which changes in the direction of the electric field, which includes all molecules except for spherical top molecules. Homonuclear diatomics, H2, N2, and so on, they will cause change in polarizability. So they are Raman active, but there is no net permanent dipole moment. Hence, they are microwave inactive. Spherical top molecules like CH4, SiH4, silane, is methane, silane, etc. are Raman inactive because the rotation will not produce any change in polarizability. So this is about the vibrational Raman spectrum. Vibration modes which cause a change in polarizability of the molecule will be Raman active. Homonuclear diatomic molecules like H2, N2, Cl2, etc. show changes in the polarizability. Hence they are Raman active. Homonuclear diatomic molecules will show Raman spectrum. However, there is no change in dipole moment. Hence they are IR inactive.